So when you write a line of code to log something, what do you actually picture in your head? For most of us, it's just a simple message, right? Printing to a file or onto a screen. It feels instantaneous, basically free. But what if I told you that simple picture is, well, completely wrong? That single line of code is hiding a whole world of complexity. Let's dig in and see what's really going on.
This right here, this is the core assumption that trips up so many developers. We sprinkle our code with debug and trace logs, thinking, hey, if they're turned off in production, they just disappear. But they don't, not really. And that hidden cost, it can be a really big deal.
Okay, so if it's not just printing, what is happening under the hood? Every single time your code makes that call to the logger, what are we paying for, even when nothing shows up on the screen? To really get the cost, you first have to realize that logging isn't just one action. Nope, it's a whole process. It's actually a pipeline with multiple stages, and every single one of those stages has an impact on your application's performance. Yeah, think of it like a little assembly line. Your log message has to get checked, filtered, formatted, and then finally handed off to the operating system to actually be written somewhere. It is way more involved than a simple print statement. So let's do this. Let's follow a single log event on its journey. By tracing its path from start to finish, we can see exactly where all those hidden costs are hiding, pretty much in plain sight. It all kicks off when your application creates a log event. The logger grabs it, and right away it hits a level filter. This is the first gatekeeper, asking, is this message important enough to continue? If it gets the green light, it moves on to the formatter, which turns it into a nice, readable string. From there, it's handed to an appender. That's just a fancy name for the thing that sends the log to its final destination, like a file. And finally, the appender has to talk to the operating system to actually write the data. Every single one of these steps consumes resources and is a potential performance bottleneck. All right, now that we've seen the whole journey, let's zoom in on the two biggest culprits for performance problems. These are the ones that bite you even before a single character gets written. Check this out. It's all about when the work happens. On the left, with that plus sign, the program eagerly builds the full string, user Alice, and allocates memory for it before the logger even checks if debug is turned on. So if it's disabled, well, you just wasted CPU cycles for absolutely nothing. The approach on the right, though, that's lazy. It's smart. It just passes the raw pieces to the logger and lets it figure things out later. And this is the magic right here. Using those little curly brace placeholders isn't just about making your code look cleaner. No, it's a performance feature. The logger checks the level first, and only if the message is actually going to be logged does it spend any time building the final string. All that wasted work we just saw, poof, gone. All right, on to the second major performance leak. We all love seeing the exact file and line number in our logs, right? It's super helpful. But have you ever stopped to wonder, how does the logger actually find that information? The answer can be surprisingly expensive. What we're looking at here are two totally different philosophies. In languages like Java and Python, finding where a log came from is a runtime thing. The program literally has to pause, look at the entire chain of function calls, the call stack, and walk backwards to figure it out. It's slow. But in languages like C++ and Rust, this whole problem is solved before the program even runs. The compiler just bakes the file and line number right into the code as plain text. The cost at runtime? Absolutely nothing. Zero. So to fix all these performance issues, a lot of us turn to asynchronous logging. And it seems like a silver bullet, right? Our app feels snappier, the logs still show up, everything is great. But this supposedly free lunch has a hidden price tag. And look, the benefits are real. You can't deny them. When your application logs something asynchronously, it basically just drops the message into a box and moves on instantly. The latency it feels is super low. Then a background worker comes along and does the slow work of writing to the disk. This lets your main application handle a lot more traffic. This is the question we always forget to ask. Asynchronous logging fundamentally changes the rules of the game. What guarantee do you actually have that your log message will be saved when things go sideways? Here's the gamble you're making. You are trading durability for speed. Those log messages are just sitting in a temporary line, an in-memory queue. If your application suddenly crashes, boom, every message in that queue is gone forever. Even worse, under heavy load, that queue can fill up. And to prevent the whole system from falling over, the logger will just start throwing away messages. And you risk losing the exact breadcrumbs you'd need to figure out why the system was struggling in the first place. These trade-offs aren't just about which logging library you picked. They go deeper. They're fundamental design decisions baked right into the programming languages we use every day. You inherit these choices whether you realize it or not. At its core, it all comes down to this one conflict. Does the language prioritize giving you the flexibility to change things while the program is running, or does it prioritize making sure that disabled features have absolutely zero cost? You can't always get both. Take a look at this table. You can see it all laid out. That caller detection column, that's the runtime versus compile time split we were just talking about. But the really important column, the game changer, is the one on the far right, compile time elimination. And notice the huge difference. For languages like Java, Go, and Python, the answer is a flat no. But for C++ and Rust, it's a yes. And this is the ultimate payoff of that design choice. In C++ and Rust, if you disable trace logging when you compile, those log calls aren't just skipped. They are erased from the final program. They literally cease to exist. But in Java and Python, even a disabled log call results in a tiny little if check that runs every single time. And in a really hot loop, that can add up. Okay, so knowing all these costs and trade-offs, how do we get smarter about this? How can we be more intentional with our logging? It's about thinking beyond just choosing a log level. One really powerful tool that's often overlooked, especially in the Java world, is the marker. So instead of just filtering on severity, like info or error, a marker lets you tag a log with a category. You can say, hey, this is a security event, or this is a billing event. And then you can configure your system to say, route all billing events to a special file, no matter if they're info or warrant. It gives you multi-dimensional logging. It's super useful. So let's wrap this all up. The big thing to remember is that a disabled log call is not free. You pay a price for building strings too early, which is why those placeholders are a genuine performance feature, not just nice syntax. You pay a price for speed with async logging, you trade durability for throughput, and you might lose the most important logs right when you need them. And remember, a lot of these costs are just baked into the design of your programming language. I'll just leave you with this final thought. When your system is on fire and everything is going wrong, your logs are the only story you have to figure out what happened. After everything we've talked about, are you sure you're set up to record the right story?